Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. Today's topic is hydrogen spectrum from the chapter atomic structure. So, Niels Bohr, scientist named Niels Bohr, was awarded Nobel Prize for explaining this hydrogen emission spectrum. As he explained successfully hydrogen spectrum, he was awarded Nobel Prize. So this hydrogen spectrum is a type of emission spectrum. What is this? This is emission spectrum. Emission spectrum. Emission means absorption, emission, opposite of absorption, releasing. Okay, that is emission. Emitting, right? So, what did he do, Niels Bohr? He took hydrogen gas in the discharge tube. See, this is discharge tube. Here, an apparatus is seen. And what is this? Discharge tube. In this discharge tube, he took hydrogen gas and he applied very high potential by applying high potential. How high potential can be applied into this discharge tube? High potential means creating high potential difference. High potential difference can be created by using batteries. So by using here batteries, a very high potential is created in this discharge tube in which hydrogen gas is taken. So when high potential is applied, it is found that a bright light is obtained. A bright light is obtained. This is bright light. So this bright light is passed through prism and made to fall on a photographic film. This is photographic film. So whatever is observed on this photographic film, and that is called as what? Hydrogen spectrum. Whatever is observed on this photographic film, and that is called as what? Hydrogen spectrum. See, this light when passed through prism, an emerging beam of light is collected over photographic film. And that is called as what? Hydrogen spectrum. It is line spectrum. So first of all, hydrogen spectrum is emission spectrum. So spectrum produced due to release of energy. Emission spectrum means spectrum or spectra produced due to energy release of energy or emitting of energy. And hydrogen spectrum is line spectrum. What is that? It is a line spectrum. What is meant by line spectrum? Here line spectrum is produced by atoms. This spectrum is characteristic of atoms in gaseous state. So atoms in gaseous state produces line spectrum. Okay, it's not a band spectrum. There are two main differences, line spectrum and band spectrum. Line spectrum is produced by atoms which are in gaseous state, whereas band spectrum is produced by molecules. So hydrogen spectrum is emission spectrum and line spectrum. So what has happened? So when very high potential difference is created, first of all, hydrogen gas is in the form of molecule. By using that energy, it gets converted into hydrogen atoms. hydrogen atom. After converting into hydrogen atoms, what happens? Where is the electron present? The electron, so this, let us consider this as stationary states 1, 2, 3, 4, 5, 6, 7. According to Niels Bohr, these are also called as what? Orbits. These are also called as orbits. This is infinity. What are these called as orbits? You are finding here. Electron is present in the first orbit, right? There is electron present. Electron is present in the first orbit. When you are passing lot of energy into the discharge tube by creating a high potential, what happens? This electron gains that energy. Depending upon the energy gained, it is excited to higher energy state. What is this first energy state called as a ground state? This first energy state is called as what? A ground state. Okay, our first orbit is called as a ground state. It is absorbing energy. Depending upon the amount of energy absorbed, what happens? It jumps to, or it get excited to higher energy state. For example, it moves to 6th energy state. Or let us take it is moving to 8th energy state. Is it stable in the 8th energy state? No. It is not stable in the 8th energy state. What does it do? It will return to the original state. When it is returning to the original state, what happens? What amount of energy it has absorbed, that amount of energy it will release. So that release of energy can be done in a single step or in more than one steps. This de-excitation happens in one step or more than in one step. There are many possibilities here. For example, let us take here electron is in 8th energy state. It is returning to the first energy state. It can return directly from 8th energy state to first energy state. So when it is in the 8th energy state, it is having more energy. By releasing some energy, it returns to the first energy state. That released energy will be how much? The energy will be the difference of energy levels of 8th energy and first energy. That can be understood by delta E. What is that? E8 higher energy, E8 minus E1. So how much energy it has released? That energy is released in the form of spectrum or spectral line. And how much energy is associated with that spectral line? How much? It is the difference between the energy levels of 8 and 1. Because here it is returning from 8th energy level to first energy level. This is one possibility for the electron to move to the original state. There are different possibilities. See, let us see all those possibilities. It can for example, it is in the 8th. It can move to 7 first. When it returns to 7, it releases one spectral line. From 7 to 5, when it is returning, it releases one spectral line. From 5 to 2, releases one spectral line. For every de-excitation, it releases one spectral line. From 2 to finally 1. So So the electron which is present in higher energy state has different possibilities to return to the first energy state. Okay. In this discharge tube, we have taken hydrogen gas. That means there are huge number of hydrogen atoms in this discharge tube. So considering all the hydrogen atoms and their de-excitations, here electron is having many possibilities to return to the first energy level. If all those possibilities are considered, and during each de-excitation, it is releasing energy in the form of spectral line. And if all those de-excitations are considered, it is found that there are 5 series of spectral lines. So in hydrogen atom, when the electron is de-exciting from higher energy level to lower energy level, 5 series of spectral lines are discovered. And in each series, there are a group of spectral lines. See, here there are a group of spectral lines. So this group of spectral lines is called as Lyman series. And this group of spectral lines is called as Balmer series. This group of spectral lines is called as what? Paschen series. This group of spectral lines is called as what? Bracket series of spectral lines. So in this way, you can call it as P fund series or fund series. There are 5 series of spectral lines discovered considering when electron in higher energy state is returning to the lower energy state or first energy state. There are 5 series of spectral lines discovered. See, when electron is de-exciting from higher energy state directly to first energy state. See, 2 to 1. What is that? 2 to 1. Here 3 to 1. Here 4 to 1. 5 to 1. 6 to 1. Directly from higher energy state to first energy state 1. In this way 7 to 1, considering infinity to 1 also. Okay. So if the electron is de-exciting from higher energy state directly to the first energy state, whatever the spectral lines produced, spectral line means the energy released when it is de-exciting is released in the form of a spectral line or spectral line. All those series of spectral lines is discovered by Lyman, and those series are called as Lyman series. And these spectral line means it is having some energy. The one which is having energy, from Planck's quantum theory we have studied that E is equal to hc by lambda, or E is equal to h nu. For every energy you are having some wavelength associated with it. For every energy there is some frequency associated with it. That means this spectral line, as it is having energy, it is associated with the wavelength as well as it is associated with some frequency. So their wavelengths or frequencies lies in the range of UV region. Electromagnetic spectrum we have studied. In that electromagnetic spectrum there is UV region, UV region has a range of wavelength, a range of frequency. These spectral lines, their frequencies or wavelengths, they lie in UV region. They lie in the UV region. So that is Lyman series. Next is Balmer series. When the electron is de-exciting from higher energy directly to second energy state, from higher energy level to second energy level, from higher energy level directly to second energy level, then series of spectral lines produced, that is group of spectral lines produced are found are called as what? Balmer series. Will the electron stop at the second energy level during its de-excitation? No. It will finally move to the first energy level. See, second to first energy level already we have seen in Lyman series. Second energy level de-excitation to first energy level electron de-excitation is already studied in Lyman series. We are speaking about the electron de-exciting from higher energy directly to the second energy level. That's called as what? The Balmer series. See, these Balmer series spectral lines, already we have studied that they are having energy, and energy is associated with wavelength as well as frequency, and their wavelengths lies in the range of visible region. Visible region. Okay. Right. The only series visible to the naked eye is termed as visible region of hydrogen spectrum. In the electromagnetic spectrum also we have seen that there are different rays, ultraviolet rays, infrared rays, gamma rays, cosmic rays, and among all those rays, only a region or a range of wavelength is visible, and that's called as visible region. Okay, in this visible region we have 7 colors also we have seen, VIBGR colors. Okay, Balmer series. Balmer series. What is Balmer series? When electron is de-exciting from higher energy level to second energy level directly, the series of spectral lines produced, their wavelengths or frequencies lies in visible region, and that group of spectral lines is called as what? Balmer series. In the same way, when electrons de-excite from higher energy level directly to third energy level, from the third energy level, later it moves to first energy level. So 3 to 2 already we have seen that you are finding in Balmer series, and 2 to 1 you are finding in Lyman series. But when electron is de-excited directly to third energy level, then that series of spectral lines is called as Paschen series, and it lies in near infrared region, IR region. These three series lies in infrared region, where Paschen series is near infrared and Fund series is far infrared. Because infrared region is having a range of wavelengths or range of frequencies. Right? So when the electron de-excites from fourth energy level directly to higher energy level directly to fourth energy level, then a series of spectral lines, that group of spectral lines is called as a bracket series. And when electron de-excites from higher energy to fifth energy level, then the series of spectral lines is called as a Fund series. So considering all the possible de-excitations in the hydrogen atom, that means in the hydrogen gas there are several hydrogen atoms. All those several hydrogen atoms are considered, and when all the possible de-excitations are considered, then we are finding 5 types of series. Those are Lyman series, Balmer series, Paschen series, bracket, and fund. Okay. Let us see. Different series of spectral lines in hydrogen emission spectrum. So one is a Lyman series, Balmer series, Paschen series, bracket series, fund series, right? So here there is a Rydberg equation, Rydberg equation or formula to calculate the wave number of the spectral line in this series. What is that formula? Wave number is equal to RH into Z square 1 by N1 square minus 1 by N2 square. Okay. Where RH is called as Rydberg constant, Z is atomic number. Okay. So N1 and N2, we will later discuss this equation or formula to calculate the wave number of the spectral line produced in the hydrogen spectrum. So you are finding N1 is equal to, here N1 you are finding, N1 is equal to 1 always for Lyman series. N2 can be 2, 3, 4, 5, 6, 7, whatever it is, up to infinity. In Balmer series, N1 is always equal to 2 and N2 will be 3, 4, 5, 6, 7 because it is de-exciting from higher energy state. In Balmer series, to which energy state the electron is coming to? It is coming to second energy state. So finally it is coming to second energy state. In Paschen series, electron is coming to third energy state. So N1 is equal to 3. Right? So in bracket series, electron is coming to fourth energy state. So N1 is equal to 4. So when you are applying N1 and N2 in this formula, Rydberg equation or Rydberg formula, for fund series, N1 is equal to 5, right? Let us see. In every series, for example, let us take Lyman series. So Lyman series 1, 2, 3, 4, in this way we are taking to infinity. What is this? Infinity. What series is this? Lyman series. For example, it is Lyman series. In Lyman series 1, 2, 3, 4. When electron de-excites from second energy level to first energy level, and this is called as a first line. What is this? First line. And when electron, first line means N1 is equal to 1, N2 is equal to 2. When you are substituting in this Rydberg formula. Let us take next line. When electron de-excites from 3 to 1, and that is called as what? It's called as what? Second line. Second line. So N1 is equal to 1, N2 is equal to 3. 3 to 1. What will be third line? Next higher energy state. From 4 to 1, electron is de-excited. What is this third line? Third line. N1 is equal to 1, N2 is equal to In this way, when electron is de-exciting from infinity, last line, what is that called as a last line or limiting line. After that, we don't have any line. Last line or limiting line. Then n1 is equal to 1, n2 is equal to infinity. This is all for what? Lyman series. The same can be applied for Balmer series. Same can be applied for Balmer series. Right? For example, let us take Balmer series. Balmer series. 1, 2, 3, 4, 5, infinity. 1, 2, 3, 4, 5. When electron get de-excited, what is this? Balmer series. When electron get de-excited from 3 to 2, in Balmer series, electron de-excites from higher energy level to second energy level, and that is called as 3 to 2 is called as first line. First line in Balmer series is also called as H alpha line. What is that also called as a H alpha line? So in this, n1 will be equal to 2, n2 is equal to 3. Second line, what is that called as H beta line? n1 is equal to 2, n2 is equal to 4. Third line, like alpha, beta, gamma, n1 is equal to 2, n2 is equal to 5. So in this way, from the third to 2, it is first line, 4 to 2 second line, 5 to 2 third line. It's also called as H alpha, H beta, and it is called as a H gamma, H delta, in that way. Then last line, or which is also called as a limiting line. And what is that called as a limiting line? So for whatever the series, for all series it applies. For all series of spectral lines, what is last line? Last line means electron de-exciting from infinity. N2 will be infinity. N2 will be infinity. Last line or limiting line. So this is applicable for every series. Okay. So in Lyman series of spectral lines lies in ultraviolet region, Balmer series visible, Paschen series near infrared, bracket series, fund series far infrared. Okay. Next, maximum number of spectral lines produced when an electron jumps from n2 to n1 state for a simple atom. So in the discharge tube, there are a huge number of hydrogen atoms. When all those de-excitations are considered, maximum number of spectral lines produced. Maximum number of spectral lines. Maximum number of spectral lines produced when electron is de-excited. For example, let us take electron is de-exciting from 5th energy level. 1, 2, 3, 4, 5. Okay. 5th energy level to 1st energy level. What are those possibilities? Let us take 5 to 1 directly. Otherwise, 5 to 4 and 4 to 1 directly. or otherwise 5 to 4 it came. There is possibility for 5 to 3 also. 5 to 3 and 3 to 1. There is possibility for 5 to 2. 5 to 2 and 2 to 1. Okay. So all the possibilities let us see. See, the 5 to 4. 4 to 2 is also possible. After coming to 3, 3 to 2 is also possible. After coming to 4, 4 to 3 is also possible. Right? So these are all the possible spectral lines. So count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spectral lines are possible. So maximum number of spectral lines is given by the formula. What is that? N into n plus 1 by 2, where n is equal to n2 minus n1. n2 here is 5, n1 here is 1. Formula is n2 minus n1 into n2 minus n1 plus 1 by 2. That is equal to 5 minus 1 into 5 minus 1 plus 1 by 2. That is equal to 20 by 2. That is equal to 10. So how many spectral lines? 10 spectral lines are produced. Here you are finding 10 spectral lines. And again in the examination also, you can be asked how many spectral lines are there in the Lyman series. So Lyman series spectral lines, how many are there? Lyman series 4. 1, 2, 3, 4. Balmer series, how many spectral lines are there? 5, 6, 7, 3. Passion series, how many are there? 8, 9, 2. Bracket series, how many are there? 1. Fund series, there are no spectral lines. So totally how many? 10. Got it? That is how we calculate the number of spectral lines produced when the electron de-excites from higher energy level to lower energy level. These energy levels will be given in the examination. From which energy level to which energy level the electron is de-excited. Okay. So next, number of spectral lines in a series, in a particular series, is given by n2 minus n1. For example, here it is also already there. For example, n only one series. Let us take Balmer series. In Balmer series, n2 is equal to 5, n1 is equal to 1. So n2 minus n1 is equal to 5 minus 1. That is equal to 4. See, 4 spectral lines are there. For example, let us take Balmer series. 1, 2, 3, 4, 5. Okay. So 5, 4, 3, 2, 1. How many spectral lines can be produced when electron de-excites from 5 to 1 in Balmer series? Balmer series n2 is equal to 5, n1 is equal to 2. Up to here it comes, right? So let us take 1, 2, 3. So formula is n2 minus n1, that is equal to 5 minus 2, that is equal to 3. So this is the formula for a particular series. This is the formula for maximum number of spectral lines when considering all the atoms of a particular gas taken in a discharge tube. Okay, so in the next video we shall discuss the derivation of this Rydberg formula. So this is the discussion regarding hydrogen emission spectrum. Thank you for watching. We shall meet in the next class.